Alright guys, quick video over population practice problems. Figure do a few of these. You guys can try some. Hope y'all are doing well. So at number 1, we're looking at suppose in 2015 a population of 500 squirrels lived in a chaparral region of Southern California. Every year 55 are born and 32 die. Calculate and interpret the following. What's my population growth rate? Now that's D of n over D of t. That's my growth rate, right? Population growth right here. And actually, if you take calculus, this is going to look really familiar. This is actually the derivative of n in terms of t. If you go onward in your math career and you take differential equations, you'll actually find that a lot of times you're finding out population growth rate because all these are calculus problems. Luckily for us, the rate is our slope, which is also just B minus D, births minus deaths. So if we have 55 born and 32 die, then our growth rate is 23 squirrels a year. So that tells me I would anticipate that every year I have 23 more squirrels. Ta-da! That's my population growth for that year. Now, what's the per capita growth rate? Now, my per capita growth rate means, because growth rate is dependent, ripping paper, dependent on the size of the population. Okay, I hope I hit record. I did. All right, so as the population goes up, this birth rate, if it stays constant, is going to get bigger because there's more people. All right, so what we do is we take the growth rate, which is, we're going to pretend we're going to be looking at exponential growth now, not just 1 year. We're going to do R max times n. All right. So now our R max, you have to, well, all right. So when we know our rate of growth, right, our D of n over dt, we know our rate of growth, we know our n. Let's find this growth rate per capita style. So our dn over dt is 23 times R max times n, which is 500. So I'm going to divide both sides by 500, and I get 23 over 500 equals my R max, also known as 0.046. So that means we expect an increase of 4.6% every year. This is going to be more accurate, right? Because this is growth. Because as there's more squirrels mating, we have a positive growth rate. So we're going to go by percent, not by 23 squirrels a year, because that's not going to be consistent. All right. So we expect 4.6% more squirrels every year. Squirrely Dan. Now let's actually do the problem then. So we expect 4.6% more squirrels every year. We know in 2015 we had 500 squirrels. So what I'm going to do is I'm going to times it by 1.046 because I'm increasing. It's kind of like sales tax. If you want to know how much something costs, you times it by 1.06 and they'll tell you the new cost. If I multiply this by 1.046, it'll give me the new population in 2016. So population in 2016, I multiply, I get 523, which is good because that's what we calculated out earlier. Then I'll multiply this by 1.046, and I get 547. Then I multiply this by 1.046, and I get 572. I multiply this by 1.046, and I get 598. Let's graph this beast. Label your axes appropriately. This is where you're going to get your points from. So down here I'm going to put year. Put my 2015. Actually, I'm going to go every two. 2016. This is worth 1 point on the AP test, y'all. Oh my gosh. I should have blown this up bigger. Now, Very, very important. Never start with 0 over here. Never start on a number other than 0 because that actually messes with your graph. So I'm going to go up by 100 every time. So I'm going to do 100, 200, 300, 400, 500, 600. Again, you got to start your y-axis at 0. All right? Eve stats especially. You can't start another time because that will actually change the shape of your graph. So in 2015, we had 500. In 2016, we had 523, so a little bit more. Actually, it'll be right in the middle. 2017, 540. Each one of these is 50. 2018, 570. 2019, pretty close to 600. Well, I kind of messed up here. 2019 should have been right here. Oopsie schnoodle. That's why they make erasers, guys. We don't have mistakes, just happy accidents. There you go. There's my graph. That's probably like worth 4 points right there on the AP test out of 10. That's huge for the program. All right. Keep moving forward, I reckon. Hypothetically. Oh my gosh, a phone call. Sorry about that interruption. So, we have a carrying capacity of 1,500 people. Our max is 1. Population. What is the population growth rate for a size of 1,800 individuals? Right now, just by looking at this and thinking about it, if my carrying capacity is 1,500 and I have 1,800, my population's going to go down, right? Because I'm going to approach that carrying capacity. So let's fill in some stuff we know, though. So I know K, based on the formulas up above, is 1,500. My R max is 1. My N is 1,800. So I'm going to use all that information, and what I'm looking for is my dN over dt, my change in population over my change in time. Well, I know this equals R max times N times K minus N over K, because I have it memorized, right? No, it's in my formulas up above, guys. It's given to you. So now plug in stuff. My R max is 1.0. My N is 1,800. I do 1,500 minus 1,800 over my 1,500. Okay, I'm just plugging in my formula here. And when I plug this in, I get my d of n over d of t is negative 360. So that means my population is declining. Okay? Since that's negative, my population is dropping. Alright? The population is declining. Alright, good talk. Let's keep on trucking. Oopsie. Alright, look at them deer. I have no idea what's going on. So, there's 65,000 deer. The carrying capacity is A2,000. We're going to assume R max is 1.0. And let's answer the following. So, is it above or below carrying capacity? That's our N. This is our carrying capacity. We are below carrying capacity. Right? Alright, what's going to be my growth rate in 2016? If you're feeling good about this, try it on your own and see if your answer matches up with mine. But we're going to do change in numbers over change in time equals R max. R max, max, X, N times our K minus N over K. All right. So let's plug in what we know. Our R max is 1.0. Our population is 65,000. Our carrying capacity is 82,000 minus our 65,000 all over our carrying capacity of 82,000. You silly goose. And when I do that, I got 13,476 deer a year. Because it's population over time. I spelled deer wrong. My dearies. All right. So then what, given that now, what do I anticipate my population to be in 2017? Well, I have 65,000 deer. And I'm adding 13,000 deer a year. So I combine those and I get my 78,476 deer. Label your work. All right. All right, good talk. This next chart is gross to fill out. But we're going to do it. All right, so our population here was 65,000. Our growth rate was 13,476 from above. And when we added it, we got 78,476. Now remember, our growth rate is going to change every year because it's not an exponential growth. There's a carrying capacity. So in order to find my growth rate, I need to go through and do the whole process again where I'm doing my R max times my population times my carrying capacity minus my population all over carrying capacity. All right, and when I plug this in, I got 3,372.6. Okay? And then when I add these two together to get 2018, when I add them together, I get 81,849. Now to find my growth rate, I'm going to do my R max times my population. This looks harder than what it actually is. It's just tedious. Times my carrying capacity minus my population all over my carrying capacity. And when I did that, I got 150.7. When I add those together, I get very, very close to 82,000. And my population's 82,000, and you plug it in, you're going to get 0. If you're at carrying capacity, you're going to get a 0 population growth. All right? All right, let's graph this beast. Let's go. So we have 2016, 2017, 2018, 2019. And again, we got to start at 0, so I'm going to go 20,000, 40,000, 60,000, 80,000. So this is pop, deer pop. This is year. All right, there we go. That's 1 point right there. So 2016, we had 65,000. Here. 17, we had 78,000. Should be about here. 18, 81,000. Should be about here. 19, we had 82,000. So you see this graph is curved. Now what happens to our population size from 2016 to 2019? I would say it gets closer and closer to carrying capacity until it reaches it. Okay? Because as you approach carrying capacity, your population slows. Okay? Now, what would happen if we got rid of wolves? Would the graph, could the graph change? Yeah, I would say you're at carrying capacity, you remove wolves, your carrying capacity is going to increase, so that graph's going to get a little bit higher. All right, so it's going to go up again until carrying capacity is once again reached. All right, guys, I hope this was helpful. Hope you guys are doing okay. Email me any questions. Bye.